There is something happening right now, at this exact moment, that no telescope can see, no clock can measure, and no human intuition was ever built to accept. And it isn't happening in some distant corner of the universe. It's happening inside the structure of time itself, inside every second you've ever lived through. And black holes are the place where it stops being subtle. Here's the thing about black holes that almost no one tells you plainly. They are not the mystery. They are the place where the mystery becomes impossible to ignore. Because what black holes actually reveal, when you follow the physics all the way to its most uncomfortable, is that reality is constructed from limits. Precise, non-negotiable, structurally necessary limits. And nearly every phenomenon in physics that feels like magic, like a violation of common sense, like something that shouldn't be allowed, is just one of those limits dressed up as a paradox. That's the argument here, not the science fiction version, the real one. Start with something that sounds almost too simple to matter. Right now, you and someone sitting on the opposite side of the planet are not sharing the same present moment. That sentence usually gets dismissed as philosophy, as metaphor. It isn't. It is a geometric consequence of how space-time is structured. Your now and their now are physically tilted relative to each other by a measurable angle determined by your velocity and the gravitational field you're sitting in. Two observers moving differently don't just see different. They genuinely disagree in a measurable way about which events are happening simultaneously. Neither is confused, neither is wrong. There is no universal now ticking away somewhere behind the scenes. There is only local time, local geometry, and the human habit of assuming everyone shares the same clock. Picture it like two sheets of paper, both representing space-time, each tilted slightly relative to the other. What counts as the present on one sheet cuts diagonally across the other. The faster you move, the steeper the tilt. The stronger the gravity you're inside, the more compressed the time axis becomes. These aren't poetic analogies, they're the geometry. Notice how your intuition resists this. It wants there to be one master clock ticking somewhere. There isn't, and that resistance is exactly the feeling we're going to keep following, because it leads directly to black holes. Here's the first question to carry with you. If the structure of time depends on your position and velocity, what happens to time's structure when gravity becomes so extreme that even the geometry of the future gets pulled in one direction? One of the most persistent misconceptions about black holes is that they're cosmic vacuum cleaners, that they actively suck matter inward the way a drain pulls water. They don't. A black hole is a region where space-time geometry has curved so severely that every possible future-pointing path, every direction any particle or beam of light could physically travel, leads inward. There is no force yanking you. Space itself is oriented that. If you replaced the sun with a black hole of identical mass, Earth's orbit would not change by a single meter. We'd freeze in the dark, but we would not spiral inward. The danger of a black hole has nothing to do with unusual gravity at distance. The danger is what happens when you get close enough that the geometry shifts beneath you. And here's what that shift actually means inside the event horizon. In normal space-time, time moves forward and space extends outward in all directions. You can choose which direction in space to move, but you can't choose whether time advances. Once you cross a black hole's event horizon, those roles swap. The radially inward direction becomes your future. It isn't that you're being pulled, it's that inward is the only direction time is pointing. Choosing to go outward, once inside, would be as physically meaningless as choosing to move backward in time. This isn't dramatization. It falls directly out of the mathematics of general relativity. Now, what does time actually look like at the event horizon for someone watching from a safe distance? Pause and predict what happens next. If time slows down near massive objects, and a black hole is the most extreme concentration of mass energy possible, what would an outside observer see happening to someone falling in? What you'd actually see is this. As your friend falls toward the horizon, the light they emit has to climb out of an increasingly deep gravitational well to reach you. Each wave of light takes slightly longer to escape than the last. The light gets stretched toward the red end of the spectrum, gravitational redshift, and the image dims, seconds, fading toward infrared, then radio, then into silence. In theory, the final photons your friend emits just before crossing would take infinite time to reach you, which is why mathematically it appears to freeze. But practically, the image doesn't freeze dramatically and hold. It dims and reddens and vanishes, like a signal fading from a dying radio station. Your friend doesn't freeze. From their frame of reference, they cross the horizon smoothly. Their own clock keeps ticking. There is no dramatic jolt, no wall, no alarm. The misconception is that one of these experiences is real and the other is an illusion. Physics says both are equally valid descriptions within their own reference frames. Two observers, same event, completely irreconcilable experiences of time. Neither is wrong. The limit, the speed of light, the causal structure of spacetime, is what enforces both views simultaneously, without contradiction. Now, about the physical experience of crossing the horizon. This is where a detail almost always gets skipped. If you fell into a stellar mass black hole, the type formed when a single massive star collapses, with a mass maybe 10 or 20 times the sun. Tidal forces would kill you before you ever reached the horizon. The difference in gravitational pull between your head and your feet, across even a few meters, would be catastrophic. The technical term is spaghettification, and it is exactly what it sounds like, but a supermassive black hole, the kind sitting at the center of galaxies, millions or billions of solar masses. Has its event horizon so far from its center that tidal forces at the horizon are relatively gentle. You could cross it without feeling much of anything. The peril from tidal forces would come later as you fell inward toward the singularity. The bigger the black hole, the more survivable. Briefly, the crossing. And we know these objects are real. Not theoretically real, photographically real. In 2019, the Event Horizon Telescope, a global network of synchronized radio dishes, captured the first direct image of a black hole's shadow, M87, a black hole 6.5 billion times the mass of the Sun, 55 million light-years away, in 2022. The same collaboration imaged SCRA, the black hole at the center of our own galaxy. These aren't artist renderings, they're data. Light bending around a region of space-time so curved that no light escapes it. And in 2015, LIGO detected gravitational waves, ripples in space-time itself, from two black holes merging over a billion light-years away, an event lasting fractions of a second that released more energy than all the stars in the visible universe combined. At that moment, the universe didn't ask our permission before doing something that extreme. Here's the second open question to carry. If a singularity forms at the center of a black hole, does physics actually break down inside it? Or does something else happen that we don't yet have the mathematics to describe? Almost certainly the second one. A singularity in general relativity, a point of infinite density, infinite curvature, is almost universally read by working physicists not as a real feature of the universe, but as a red flag. It's what happens when a theory is applied beyond the range where it remains valid. The same way Newtonian mechanics works beautifully until you get to the atom, and then quantum mechanics takes over. General relativity likely hits its limit at extreme density, and whatever takes over from it will describe something finite, strange, but physically real. The universe keeps doing something, and we just don't have the right language yet. This is where quantum gravity enters. Candidate frameworks, loop quantum gravity, string theory, and others each make different predictions about what replaces the singularity. String theory, for instance, offers the idea of fuzzballs, quantum objects where the matter that collapsed is spread across a stringy structure rather than compressed to a point, and no sharp singularity ever forms. There's also the firewall debate, a fierce argument, still ongoing, over whether quantum mechanics forces a wall of high-energy radiation just inside the horizon, which would make the crossing anything but smooth. These are unsettled questions, but they point in a consistent direction. The singularity is a placeholder for ignorance, not a feature of reality. Which brings us to Hawking radiation, and another misconception worth addressing carefully. The popular description goes something like this. Virtual particle-antiparticle pairs pop into existence at the event horizon. One falls in, one escapes, and the black hole slowly loses mass. That story is intuitive but technically misleading. It was Hawking's own pedagogical shortcut, and physicists have been gently correcting it for decades. The actual calculation is rooted in how quantum fields behave in curved spacetime. Vacuum fluctuations, the quantum uncertainty of empty space, get mixed up by the geometry of the horizon, and the result is that a distant observer receives a faint thermal blow of radiation that wasn't there before the black hole formed. The mechanism is genuinely subtle. What matters physically is this: black holes do radiate, they do slowly lose mass, and over timescales so enormous they make the current age of the universe look brief. They evaporate. This leads directly to the information paradox. And here's where an update matters. Hawking's original argument was that information about everything that fell into a black hole was permanently destroyed when it evaporated, which would violate a fundamental principle of quantum mechanics. For years, this was a fierce, open conflict, but the scientific landscape has shifted. The dominant view today, supported by approaches like the ADS-CFT correspondence and holography, is that information is not destroyed. The Page curve, a theoretical prediction about how quantum information should behave over a black hole's lifetime, has been reproduced by multiple independent approaches, suggesting that information is subtly encoded in the Hawking radiation as the black hole evaporates, scrambled nearly beyond recovery, but not erased. The question has migrated from whether information is preserved to precisely how it's preserved, and that is a very different kind of puzzle. Not a crisis, a research program. Now for a real-world anchor that brings all of this down to something you interact with daily. GPS satellites orbit roughly 20,000 kilometers above Earth. At that altitude, gravity is weaker, so according to general relativity, their clocks run slightly faster than clocks on the surface. Simultaneously, those satellites are moving at high speed relative to you, which according to special relativity causes their clocks to run slightly slower. These effects work in opposite directions and do not cancel out. The net result is that satellite clocks drift from ground clocks by about 38 microseconds per day. That sounds negligible, but GPS accuracy depends on timing at the nanosecond level, without correcting for relativistic effects, the exact same physics that governs black hole event horizons. Your navigation would drift by roughly 11 kilometers every single day. Every successful journey you've navigated with GPS is a quiet proof that space-time geometry is not a theoretical abstraction. It's load-bearing infrastructure. This is the thing about limits in physics. They are not exotic. They are everywhere. The speed of light being constant isn't just a rule about fast rockets. It's what makes causality possible. What ensures that causes come before effects. That information propagates in one direction through time, that the universe can be internally consistent at all. Every hard limit in physics is a structural feature of reality. Remove the speed limit and causality collapses. Remove quantum uncertainty and atoms become impossible. Remove the equivalence principle and general relativity dissolves. The limits are not failures, they are the architecture. Black holes don't break physics. They push physics far enough that the architecture becomes visible. They are the place where the rules stop being invisible background and start being the only thing that matters, where the geometry of space-time isn't a metaphor but a physical object that can be imaged, measured, detected in gravitational wave signatures, and eventually, perhaps, understood all the way down to the quantum level. The universe is not infinite and chaotic. It is precise, constrained, internally consistent in a way that borders on unreasonable. The fact that a network of radio dishes spread across the surface of one small planet can photograph the shadow of a 6 billion solar mass object 55 million light-years away, and that the image matches the predictions of equations written a century ago by a man with chalk and paper. That is not magic. That's something rarer than magic. That's structure. And the deepest thing black holes show us is this: every boundary in physics is also a law. Every mystery is a limit revealing itself. And if there is something that feels like a war in the equations, a singularity, a horizon, a place where the math goes silent, it is not the universe failing. It is the universe telling you, as clearly as physics knows how, that you have reached the edge of one description, and that something more precise, more complete, and almost certainly stranger than you expect is waiting on the other side. The question isn't whether reality has limits. The question is whether you're standing close enough to one to finally see what's beyond it.